Okay, so good morning all, and thanks for having me. Hopefully I won't fall asleep in the middle of this. Jet lag is really difficult to cope with coming down here. But today, what am I going to talk about? Well, I want to talk about code. So hopefully most people here are passionate about code. I am, but I'm going to talk about this in two senses. One is the sense that we're all typically thinking about programming, writing our code, but also where does that word come from? Like, what drives it? Why do we call it code in the first place? I'm going to talk about some of the origin of it. So where the concept of having a code comes from, codes of behavior, codes of how we should interact, our manners, our etiquette, things like that, and how that impacts on our code itself. And I'll show how some of this can influence and how it works together. So one of my own personal codes is I don't like to drink bad coffee. Bad coffee is terrible. And the first time I came down to Australia, I must admit I was secretly very worried. So I've noticed that one of the things that happens here is you copy a lot of things from America at times, and Americans have terrible coffee. So I came down here and I thought, this is the land where they also said data. Sorry, it's data. So I thought, hang on, you said data, that means I'm probably going to get really, really bad coffee down here. So you kind of think, well, how do I prepare? How do I cope if I'm going to be in a hotel and I'm going to have bad coffee? Well, one of my techniques for getting by in a hotel. See, the thing is, like, as developers, we're creative. We can't help it. In fact, many software systems I've seen end up looking a bit like this, where we kind of make things kind of work, give it a duct tape. So, like, I like to run, so, like, I bring my trainers and, like, I bring a coffee pot to some places, and usually there's an iron in a hotel room, so that's a good use for it. I generally find that we can sort of brew our coffee because they don't give us a means of heating up our coffee pot in some other ways. Well, so what do we do with our code? We get to do some really quite cool and interesting things, like whenever we have well-organized things and we have the right interactions, and we can do amazing things when lots of people work together, because no one individual can do anything really impressive on their own. Right. This year, we got to have this photograph, which is actually very cool. It looks like a simple little thing, but it's actually our first picture ever of a black hole. That involved 8 telescopes all around the world. And the data for it was collected much sooner than it was actually available. One of the problems why we got to see it a little bit later than we would like to is one of those telescopes was in Antarctica. And there was so much data. We're talking about 5 petabytes of data to generate this picture. And that is hundreds of kilograms of disks that needed to be shipped, because transferring that data is not easy. Well, so imagine you're in Antarctica. Your Wi-Fi connection doesn't really be that good for shifting lots of data. So they have to actually ship the disks, physically ship them. And during the winter, it's not a place we want to fly in and out of. So there's a code of behaviors. You don't land aircraft in Antarctica in the winter. Now, one of the things that's interesting that's come out of this, so the way those sort of photographs are taken is you take a lot of photographs of all very poor quality, and then we use software to refine it and distill the essence out, and we eventually get something that's nice and crisp. Now, think about codes of conduct for a second. This is an amazing piece of software that's given us black holes. What else have we now done with that? People are now starting to take that software, take photographs from hundreds of meters away of people's keys, and using that to get a detailed picture of someone's keys where they can actually copy the keys and break into locks. I think our industry has some interesting questions to answer about what we do with some of the technology that we produce, and do we just like create cool stuff, think it's kind of fun? That's the kind of little sort of side thing from when we start to think about codes. But I'll talk a little bit about protocols and what they have for software development. We hear this term a lot. We often misuse words a lot in our industry. But I want to explore how significant are protocols to software development itself. So let's actually go back to the dictionary and look at what is a protocol. One of the reasons I care a lot about this is I'm dyslexic, and so I struggle a lot with words. One of the things I often do whenever I'm picking up any new subject is I start looking up the words in a dictionary. I always do this to find out what's the true essence, and I find we misuse stuff all of the time. Now, we got things like Google protocol buffers. Sorry, they're not actually a protocol. Google protocol buffers are an encoding, so it's kind of classic of our industry, misnaming things. One of my favorites is RAM, random access memory. I don't want memory that's going to give me something random. I want something very specific and an address. It should be named arbitrary access memory. That's just me being a little bit too pedantic. But it's kind of important. So a protocol, like we look at it, what is it? It's a code prescribing a strict adherence to a correct etiquette and precedence. Etiquette we kind of can grok a little bit. Precedence is really interesting and important in this. So the order in which things happen is very important, and that's actually key to a protocol, and we'll explore that quite a bit. The sort of technical side that we often see, we're talking about a set of conventions governing the treatment and formatting of data in an electronic communication system. We often just think of the formatting, we miss the treatment, we miss the etiquette, the precedence. These are some of the really important things. So before we get right into the technology, I want to wind right back in history and look at where some of this comes from. So where do we use codes and protocols and etiquette in some of our history, and where does it come from? Now, there's some really interesting work back done by Charles Darwin. A few people may have heard of him, sort of origin of the species and stuff. One of his other subjects that he was highly passionate about was understanding how people would interact and how they use facial expressions and behavior to drive how they interacted. And he did a lot of studies on this and discovered that independent of language, and it went even further than just learned behavior, we have instincts that helps us interact and we can tell things. So for example, shame, disgust, joy, concepts like that, we don't need to have them translated. We can see from people's behavior. And you know what? We don't even learn that because it's been observed in young children, it's been observed in people who are blind, it's been observed in some people who have unfortunately been brought up feral, that we all understand disgust. So things like that. So we can see that. So we interact with each other, and some of these behaviors helps us understand that. So this is kind of neurological to us, and we have evolved it over time. So it takes on into things like manners and etiquette. Etiquette is an old French word. It means little card or little note. So we've all heard this sort of things about keep off the grass. Well, that started at the Palace of Versailles, and Louis XIV was making it clear to people how they should behave. And so this is where some of that stuff comes from. But as a society, we can start to function, we can scale, and we can do things on a larger scale because of some of these things. Manners, sort of etiquette, courtesy, different things. This is how we function at any sort of level of scale. And it's an interesting subject that you can dig into and study. The kind of quick summary of it, there's 3 layers to it. At the most basic layer, we have what are known as our hygiene style manners, our hygiene behaviors. And these are for prevention of disease. So we show disgust, it's actually hardwired into us, so we stay away from certain things because this helps prevent disease being spread. So it's kind of key and important to what we do. We then evolve things like courtesy. So being polite, letting someone else go first, offering to share, these sorts of things. Is what we're demonstrating there is that the group is more important than the individual. So if we didn't do that, we wouldn't function as a larger group. So we display these types of behavior. And this lets us sort of function at a higher level. A good example of this would be if a small group of people get divided up into different types of roles. You'll find warriors, you'll find farmers, you'll find carers, all of these different things. Now, the warriors could so easily take everything from everyone else because that's kind of their job. They're good at fighting. They can be the thugs of the group. But they're really there for protection. If they did that, there would be no farmers. Then they wouldn't feed. It wouldn't work as a unit going forward. So people kind of learn to behave in this way. The third level is where we form norms. So we start normalizing ways of doing stuff, and this brings trust. And that ultimately brings efficiencies. And we learn this from how we can have groups. When people behave in a normalized fashion, we can learn to trust them. And again, neurologically, we're hardwired to do this. So if people behave in unnatural ways, we tend not to trust them. We will be more guarded. We become less inefficient or more inefficient in our interactions. So we start to see some of this. And it's kind of fascinating how it all goes. So if someone in a group doesn't behave the way the rest of the group does, we have hardwired instincts where we want to punish them for doing that. And even worse, we punish others who observe it and they don't punish them. And it's kind of funny that we almost can't control some of this behavior. So it kind of drives a little bit of what we do. So that's the kind of sort of biological and evolutionary side of it and how it's driven some of societies. We've taken this forward into having formal protocols. One of the most interesting areas of this is how we have international formal protocols around warfare and what we can do. So rules of engagement, this is something the military understand very well. It's broken down into what's acceptable. When you go to war, not everything is acceptable because it's such a bad thing for humans to ever go to war. We want to really try and pull that back and have the minimum damage done possible. And this is now enshrined in international law. Like, a common concept that's in there is you want to create good conditions to succeed. Like, one of the things I love about sometimes going and speaking at conferences, like, I'm deeply uncomfortable up here. Like, I actually like to hide behind this. I'm a person who likes to code, but you get to meet some cool and interesting people. I got to meet General Mike Jackson at another conference where he was a keynote speaker, and he just done some amazing things where he's explaining what happens in warfare and why they go. He's one of the most recognized British generals in history, most famously for almost avoiding World War III in Kosovo, where he had a standoff with a Russian colonel who had taken an airfield, but was ordered by the Pentagon to go in and take this airfield, and he didn't follow an order from a five-star general. But at the end of it all, it sort of got resolved, and he talked about how people interact and how you give orders and different things, which is kind of fascinating. But he talked about like, how you should never try to crush an enemy. The only point ever of going to war for him was to change the mind of the other side, was to create good conditions to succeed. And so even though he was famous as a soldier, that was the absolute last thing he ever wanted to do. And so some of the laws that are around here, so like the Latin terms of jus ad bellum, jus ad bello, is about the right to go to war and how to do war rightly. And this is all codified. So we talk about the code because we codify things. We have a protocol for how we interact. Like one example is you don't just go to war. You have to follow diplomatic procedures first. You should try to avoid it. And also you've got to be proportionate. So for example, if a small country sort of destroys one of your ships and you're a superpower, you just don't go and have a nuclear attack on their capital. That is completely unacceptable. So you have to have a proportional response. So it's interesting how we code these things up. Well, how do we code things up in software? And how do we think about this? I want to talk about how components interact. And this drives a lot of how our software is. We're now working with distributed systems. We've got largely concurrent systems. To do anything at scale, it involves things interacting. One of the best places we have for good examples of this is the IETF, Internet Engineering Task Force. We have protocols specified for how different components work. This is the backbone of the internet, how it works. I love some of the different RFCs that they've put out, and the 1st of April every year they put out quite a fun RFC. One of my favorites is the Hypertext Coffee Pot Control Protocol, being someone who's obsessed by coffee. And this is kind of fun, but you can find these quite informative. I love some of the status codes, like 418 means I'm a teapot, I'm not a coffee pot. Please don't ask me to do sort of coffee style functions. A really interesting one is this. So the Holy Wars and the Plea for Peace. I don't know if anybody's ever read this one. If you've ever heard about little Indian and big Indian type integers and how they're encoded, this is the best explanation I've ever seen for it. The origin of the words that are used in that, big Indian and little Indian, it actually comes from Gulliver's Travels, so the Adventures in Lilliput, where the people went to war over which end of your egg do you eat first. You beat the big end or the little end? Is that the way you eat your eggs? And so Indianness comes from that. But this explains some of that history, but also the origin of a lot of computer science and why we encode integers the way they are, done in an incredibly fun and really great way to read. So that's a good one to go find. Again, it's a 1st of April one, 1980. I guess many people in this room was probably even born after that. Like, Another good one is the transmission of IP using avian characters. Using pigeon post to do different things. Like that goes back to 1990. That was updated with quality of service later on, and eventually brought up to date recently for IPv6. So actually learning some of this stuff can be quite good fun. And so you think like, yeah, it's kind of nerds, but it's good, and there's lots of things we can learn from some of these things in our history. And should we document our protocols is kind of an interesting question. I love to document protocols on my projects because I think it just helps my own thinking. It helps me realize how to work my way through stuff. And particularly I find this debate very often coming up as API versus protocol. Basically, I think an API is very anemic. It's a very two-dimensional view of something. It doesn't really cover most of what's important. And most important to me in this is precedence. Order in which you do things matters much more. So you think about an API, it doesn't tell you anything about precedence. It tells you what functions it can perform, but it doesn't say in which order they should be performed. It doesn't say what are exceptions, various things that are interesting. So let's take a simple example. So let's say I have a file system, and I want to interact with a file. What is my protocol I'm allowed to interact with the file? Well, I could publish an API. But it doesn't tell me as much as doing something like this. We're going to say, if I'm going to use a file, I can perform a number of operations on it. People tend to do things like this, like a pseudo-regular expression language, where I can open a file, I can follow it by 0 or more read or write operations, followed by a close. That has told me what the precedence is. Now, for files, we take that as kind of obvious. If it's not an API you're using every day, how do you know the orders in which you should use it? What do you mean? You call this and it threw an exception and you end up reporting a bug, and somebody says, well, you should have called this other thing first. Well, if you had actually just documented the order in the first place, it would have been much easier to do. And so you can then just expand it as give the order in which things have been called, list each of the functions. That's great. I find this is a so much more useful way to design an interface with a system. Give it a go. But kind of importantly as well, when you perform any one of these actions, this question is really important. What can possibly go wrong? I've had the pleasure of working with a guy who's worked on a lot of systems that are very important, like people die if his systems don't work well. He worked for NASA, for the US Air Force, and sent stuff into space. And you think like, your software could end up causing someone's life to be extinguished. This is not a good thing. So you start to think more carefully about what can possibly go wrong. How do we get stuff go right? And it's actually one of the biggest causes of software failures we have. This report here is a great read if you haven't already seen it. It sort of explores what was the things that were behind major production outages in certain types of systems. And the thing that stood out to me in this was like there's a number of different points. But 25% of the errors they find that caused a production outage were ignored error codes or exceptions. In fact, when they dug into them, many of the exceptions that were there had a to-do in the exception handler saying, we should fix this before we go into production. Like, does your real code of conduct or behavior allow you to release software that you know those sorts of problems are in? That's not very professional. So it's kind of interesting how we go forward with this. So let's look at designing a protocol and look at a realistic example of something more complicated and how we could approach it. And this is kind of where I find it's interesting between those who have a background in some of how the world works, how larger scale systems work, can come up with much more interesting algorithms than typically the nerds who've only ever worked on their own. Because I think if your whole sphere of influence, your reference frame for the world is very narrow, it means you've got a very narrow view of what you can come up with. So multicast protocols are fascinating for this because you're dealing with sending data from one point or even many points to many points. So it's a complicated interaction. It's not just a point-to-point simple thing. And if you want to design a protocol where you're going to send out data from a single source and it's going to go to many receivers, the data can get lost on the way. How do you realize that the data has been lost, and how do you end up recovering? What's the protocol you go through for that? Do you try to centrally coordinate it? Do you try to do something different in there? And this has been a problem that's been faced a number of times. And as you do it, you end up with some very obvious problems if you try to implement it. So one of them is ACK implosion. So if you realize that data can be lost, one of the ways you deal with it is you give an acknowledgement, a positive acknowledgement that you've got the data, and that's great. The problem is that doesn't scale up, because if you get more receivers, that's more things acking. So then the source can't cope with that. You've got a scaling problem. The other side of it you can go with is, well, we'll send negative acknowledgements because we'll assume it'll work most of the time, and if it doesn't work, we'll send the knack and recover from that. Well, that does work a bit better, but it still has its own problems because most loss tends to be correlated. There'll be some network device along the way, has a buffer overrun, and it starts to drop data, and that means everybody who would be downstream from that doesn't get the data, so they'll all knack, and you end up overcoming the source. So we end up with this ACK-knack implosion. Now, there was many implementations and approaches to solve this sort of problem, and it didn't really get very far until this particular paper came out. And the first name on this paper is Sally Floyd. Her and Van Jacobson are behind an awful lot of what made the internet successful. And this one particular protocol I think is really very elegant. And so she had this very simple idea that if you end up getting lost, rather than knack straight away and say, I haven't got the data, please send it to me straight away, is you do something different. What you do is you set a random timer for quite a short period of time into the future. It's usually based on what is the round trip time between you and the source. And you set that random timer. Because this is going to be correlated, others are going to have the problem as well. So they've all set the random timer. They're going to go off at slightly different times. And whenever they go off, the first one to go off will sort of say, okay, have I received this data in the meantime? No, I haven't received the data. I'll send the knack to the source to get them to retransmit the data. Others are going to have their knacks go off at different times as well as the random timers. But the first one to send it gets the data resent, and everybody else has received it. And this way it fills in for the loss, and the rest cancel their knack timers whenever they start to see the data. Now notice there is no central control to that. It's a protocol to how they should interact. Now, if you look into some of Sally's history, she has a PhD in computer science. She's got a master's in computer science. She's got degrees in physics. Her very first degree was in sociology. I think it tells you something about how sometimes people will think differently about the world with a different background. Now, this was a brilliant piece of work, but she used standard distribution. Other people then came along later and built on this idea, and they came up with the idea that, well, if we use a standard distribution, we still do get a bit of clustering around the midpoint of when the knacks can go off. If we do an exponentially weighted distribution, we skew it towards the end, but we cut off the beginning sufficiently that the probability if a knack goes out quite soon, but not from very many sources, it actually makes it more optimal. And it did. I've implemented these protocols, and it actually works beautifully well. There's no central control, there's no complexity, and it gives you really great results. And I find it fascinating that a lot of these large-scale network protocols that work well, some of the really influential people who've been involved have come from other disciplines, and surprising things like sociology have come in to deal with that. So you talk about the hard and the soft skills that Kent mentioned earlier. Sometimes the soft skills that we have been talking about in the past are way more important to making technology succeed, even in an algorithm to get it right. So kind of being aware of this, what is the interaction? So we've got quite a large subject here. Where should we focus if we want to learn about some of this? Because there's many subjects and many subtopics to this, like how we layer stuff, how we version, how we encode, how do we manage feedback within these, how we sequence, async. I'm not going to cover all of these, but I want to give you a little bit of a flavor of what are some of the subjects and topics involved in designing good protocols, and hopefully maybe inspire some people to think a little bit about it. But let's start off with sort of looking at some encoding, and I'll ask a quick question, like who cares about waste here? Those are the people who put their hands up who care about waste use text-based protocols. Do you encode stuff in JSON or XML or anything like that? I get to measure lots of real-world systems, and usually encoding in text is one of the most expensive things you'll see in a system. I often see more CPU cycles go to encoding and decoding data than doing business logic. Now, that just doesn't feel right. So kind of one thing I'd sort of think about is if you're using text-based codecs, maybe you should consider using binary codecs. They're much more efficient. And usually at this point, I'm sure many people are thinking in their own heads, but it's human readable. I'll call BS on that. Text is not human readable in a file. I know a few people who can read ASCII. I know nobody who can read UTF-8. You've got tools that can read it. That's the interesting step that's happened, is we have good tooling. We need better tooling to read binary. I've worked on projects where people have invested in the tooling to read binary, and it works really well. So often, if we're going to sort of make a decision, make sure we're attributing where the real problem is here. It's the fact that you've got a lack of tooling, not that you can read text. You have tools that can read text. It's kind of different. And you can start doing quite interesting things. Like I work on binary protocols quite often. This is a header of one of the things I worked on. And you get to do pretty ASCII art and stuff when you define it. But then you can design tools and stuff afterwards to read this to be able to deal with it. Like, there are lots of great examples out there of how to do very efficient encoding of data. SBE I've worked on, but flat buffers, Captain Puru, SEN1. There's some of these protocols, we're not talking about percentage points faster. We're talking 2 and 3 orders of magnitude more efficient than some of the text-based protocols that we just waste CPU cycles on. And again, this is one of my sort of side rants. The ITRS report that came out in 2015 shows that if we continue on our current trajectory of spending energy in data centers, by 2040, we are not going to have enough energy on the planet to feed our data centers. And that includes how we're increasing our energy production on the planet at the same time. So this whole thing of let's just throw hardware at the problem isn't going to fly anymore, and it's going to get significantly worse as we go forward. So, kind of rant over. Let's go back to versioning is an interesting subject as well. Because when we have our protocols, we want to actually version the protocols themselves. So we need to know what conversation we're having. That's a kind of obvious one. Most people kind of can get that. The messages themselves should be versioned so we know which encoding we have of it, because we can extend them, we can add new fields. So these things live. We make mistakes. We need to get better at them as we go. So whatever we've put together must be able to be versioned, must be able to be extended without doing a big upgrade everywhere, because you want to upgrade parts of your system, not upgrade other parts of the system. That gives us the ability to scale within an organization. One part of it that I've started to learn a lot more about myself and didn't appreciate before is that versioning the instances of the data starts to really matter. It can make your algorithms themselves so much simpler. So I work on distributed consensus and other network protocols, and I love how some of our protocols have gone to the point where they're designing to make them easy to understand. And that being a primary goal is a really good thing. It's almost like we get proud of the fact that we do clever things that virtually no one can understand. That's not a good thing. We should be designing things that other people can understand and building versioning in. So yeah, it was mentioned before that I worked on the disruptor. I've worked on many concurrent systems, and I've worked on things that have been really struggling with the multi-producer, multi-consumer problem. It's a design flaw whenever people end up using queues that are multi-producer, multi-consumer, and similar sorts of systems. But we have to deal with it until people learn how to design a bit better. So how do we create good algorithms for that? I've implemented a number of them myself and made mistakes in them. And having explored the whole area, I ended up having a light bulb moment when I was reading as much research around this as I could find. And I came across 1024cores.net, the work of Dmitry Yukov, and the genius in his implementation that made it so easy to understand and easy to deal with is he versioned every single state. He made the whole thing monotonic. And it, as a result, was just so much easier to reason about and work with as a result. If you're kind of interested in that sort of level of skills, like, please go read his work. I won't dig into it. But we get another interesting debate. There's the whole synchronous versus asynchronous. I think the web, in some ways, has destroyed and set back computing quite a long time. I started in the 1980s, and I've seen the advent of the web. So I was involved in the internet back when we used RN and TIN in news groups and there was no web, and then the web came along and all of a sudden we're doing document fetching. And then people sort of took this hammer and they beat every single computer science problem on the planet into the same shape, that everything is request response. So a protocol designed for fetching documents has now become the main programming model we used. And it kind of reignited RPC all over again. It's like we've had a number of generations who've run at that wall, realized that wall's got big spikes and backed off, but we've got a new generation running at the same wall again. Eventually we'll realize that it's not a good idea and probably fix it. And you just start looking at the simple mathematics of it. Like take the performance case alone. If I have a synchronous interaction, I send a request, I get a response. Like send a request, get a response. We see how time gets stretched out when we interact synchronously with something. If we change that and make the latency greater, so move things further apart, takes longer time, what we start finding is my 3 requests can't be completed in the same amount of time. We're bound by the latency of the system. And whenever we're in this phase, we're having to incur a lot of overhead. So we send a request and we have to block. We have to have the operating system get involved, suspend our threads, wait for the response, have the operating system wake us up again. That's a very high overhead. It's like trying to have a simple conversation, but you're getting the lawyers involved in everything. The overhead is very significant, and most people are not aware because they don't measure, they don't run profilers on a regular occurrence. Whereas if we go asynchronous, we can just send a request. We send another one, we send another. We don't wait for the responses straight away, and then separately, we get the responses back together again. Look how time is much more compressed. Now, if I increase the latency, does things change? Well, I can get through my 3 requests and still not have that big an impact. You can't run away from the mathematics. But for me, what's interesting is what's happening while you're waiting. Well, you can be doing other things. You're able to make progress in other areas. You don't block and wait, and you don't have to suspend them. Now we're inventing means in languages like async await and doing all sorts of stuff to get around the fact that we can't program. We can't deal with different things. So I get to teach concurrency quite regularly, and I've started noticing some patterns. A lot of the people I've found who are good at programming have something else in common. Many of them are good at cooking. That seems kind of strange. If you can do multiple things concurrently, deal with things happening at the right time and having good sequencing of time, that's exactly the same problem. We try to cram things into different ways, and again you get the, but synchronous is so much easier. It's like we're living with an industry of crybabies. Yes, some things are a little bit difficult, but you practice and you get better and you get your tooling in place. Like, if you were learning to cook and said, well, I'm going to do this and I'm going to do this, like I'm going to make a big dinner. Well, sorry, you're going to take 20 hours to do it because I'm not going to do anything concurrently. Oh yeah, but this stuff's cold, and well, I'll just heat it until it's dried out and tell people to eat it anyway. No, just don't accept that. We do this. Synchronous is blocking. It's terrible. It's kind of wrong. You got to think about we're managing state. And we can do that quite easy. We manage state, we manage it with feedback. All interactions work best when we've got the proper feedback in place. And if we're just blocking, not making progress, we can't do that. Now, we've got techniques like state machines and other things that work really nicely that have been around for a long time. But the whole abdication of responsibility and thinking about feedback is something that seems to also be a crazy thing that's happening. Like back in Claude Shannon's original paper on information theory in the 1940s, he explained the importance of feedback. We know this in everyday life. Like anybody ever sort of go home, you have a conversation with your partner and you say, can you have this done? And if you don't get a response, you don't get feedback, do you assume that agreement has happened? No, because usually that goes horribly wrong. We know the importance of the feedback, and so we practice this sort of things. But I know it's going to take time for people to think differently and work differently. So one of the things I encourage people is if you're going to design an API, start off with an asynchronous one, wrap it with a synchronous wrapper for the people who kind of cry and can't keep up yet for a bit, and sort of keep them happy, and we'll move on. But yeah, design to give the options at least, then we can do this. And we have loads of examples. we try to go down a route and then we make the mistakes and we try to fix it. So we're building RPC, we're building it often on top of HTTP, which is also built on top of TCP. And they find that this doesn't work, it doesn't scale, so we're having to do all sorts of duct tape things to try and make it right because the model is fundamentally wrong. It's like TCP has been trying to evolve through, we've added fast open to it to try and improve it. We now have quick. So if you're actually using a Google browser talking to most Google services, you're not using TCP anymore. We're typically using protocols like Speedy and HTTP2 over quick to try and make this stuff work because it gives us a much better experience. Like, we've been seeing this recently evolving through TLS 1.2 into 1.3. And a lot of it is about making things efficient, making it better. Like, that is a great spec to go read. There's some poor examples of protocols we put out there with some better examples. And even in the good ones, we start making mistakes. So one of the classic things that happened with TLS 1.3 that wasn't foreseen as a problem and then sort of becomes obvious kind of later, we have a faster way to start a connection with TLS 1.3. So we've got this zero round trip startup of a connection. This is great, it gives us a nice responsive experience, but it makes us vulnerable to replay attacks. And the only reason it makes us vulnerable to replay attacks is because the protocols that run on top of it are so badly designed. They don't consider certain things. So for example, if your protocol included a sequence number, your application protocol included a sequence number, and you get a replay attack, if you've already seen the sequence number before, you just throw it away. You're not idempotent, you're not subject to a replay attack. Whereas most people are not thinking about designing things and having that state in place. It makes quite a difference. So batching, here's another good example. Consider the etiquette of a request, and our behavior in the real world sort of shows some of our behavior with how we write systems. So imagine, let's just continue with the cooking analogy from earlier. We get invited around to a friend's house. They're going to make dinner for the evening. You're going to help out, and you arrive and say, like, I need some milk. I need to get some milk to finish the dinner. Could you go to the shops and get me the milk? You say, yeah, good friend, I'll go to the shops, get some milk. You come back again. Imagine you come back and they say, do you know what? I actually need more milk. Could you go back to the shop again and get me a bit more milk? And so you go to do that and you come back again. And you arrive back and they say, do you know what? I actually need more milk and I need some cheese. And you go back to, hey, hang on, I've come over and have a good night. Like, they're all drinking wine there and I'm running backwards and forwards to the shop. This is not kind of good. You wouldn't do that. You wouldn't do that sort of behavior. Yet we do that when we write software, going to networks, going to disks, doing whatever. Because it's an inanimate object, we don't care about it. We know it's got no feelings. We behave in this way. So, yeah, we just don't care. We actually do. This also shows the flip of humans, when they want to do nasty things, dehumanize other people. That's kind of part of what we do. I'm kind of thinking, like, I'm kind of nice to computers in general, so that whenever they kind of take over the world, I'm hoping I'm one of the people they don't come after. So start thinking a little bit. Like, yes, they don't have feelings, but we have built-in instincts to try and do the right things. Try let some of those built-in instincts actually drive some of our software design. Like, good examples of this is what's coming with 100 gigabit Ethernet. Our current APIs and current approaches cannot use 100 gigabit Ethernet properly. The Linux community is having discussions about how we change APIs. The BSD sockets API is not up to doing 100 gigabit. We're having other APIs are now evolving. So like Linux is already moving into send message, receive message. So for a single system call, let's send multiple messages, let's receive multiple messages. We get things like VMA, API, open onload, DPDK. These are all asynchronous APIs that work in user space that can drive some of these networks at the full load. And they can achieve much better things. So you can see this is where it's going. Like, if you're one of these people saying, well, I want to keep doing my synchronous protocols with text, I'm afraid you're going to be left behind in some of the future because our CPUs aren't going to get faster and keep up. Which kind of leads me into what I call snake oil protocols. And this is kind of an unfortunate thing of the corporate world is we all want an easy life. That's a kind of natural instinct. And so corporations play on this. They kind of say, I've got this product, it's a silver bullet, it will take away all of your problems that you don't have to worry about things. People are lured into this very easily. One of the great examples of this is two-phase commit, or XAA protocols. It's like, we can do distributed systems, and you don't need to worry so much about the coordination. Axia will take care of all of this. Well, if you ever read the protocols rather than just read a little bit of the blurb, you reach the heuristic section that talks about all of the potential ways it can go wrong. In fact, there's some great analysis on two-phase commit to show how poor a protocol it is. One of my favorites is this particular paper by Jim Gray and Leslie Lamport, where they talk about how it's fundamentally a broken protocol and it's wrong and we shouldn't be using it. And if you don't know who Jim Gray or Leslie Lamport is, you really need to read up a little bit on the history of our subject. But this is one quote from within that paper. Two-phase commit is not fault tolerant because it uses a single coordinator, and the failure of that coordinator can cause the entire protocol to block. It's also been formally proven to be broken. Yet we still keep using this, and especially in the corporate world, the number of banks I've seen where architects are still demanding things behave in a certain way because it allows them to abdicate responsibility, and that's just not a good thing. Another example I keep seeing is people say messaging systems are guaranteed delivery. Anybody who tells you their messaging system is guaranteed delivery, I say run away from them, because it is a complete lie. Look, it's provably wrong in so many ways, and yet people still keep trying to push this. We can do at least once delivery, or maybe 0 to once delivery. We can't do exactly once. It's not possible. It's not easy to have. But we can get around most of these things if our protocols have feedback and they manage that interaction in the right way. And we do this by recovery, so sequencing things, knowing when we've got something, knowing what position we're at so we can take over again. Like, real life is full of really good compensating protocols, and our software needs to kind of reflect that. And I often see it as we're building on layers that's below. What are the true capabilities of the layers below? What can we depend on? And we build our software being cognizant of that and sort of doing the right things and knowing where it's strong, where it's weak, and doing it in some of the right ways. So I want to kind of wrap up a little bit here and talk about, are protocols really very significant to software development? I find a few people do them really well, but the majority of people don't. And I find it kind of interesting that they don't and why it hasn't really taken off in our industry. This protocol, anybody recognize it? Scientific method, Sir Francis Bacon's work, popularized by Newton. Been around a little while, kind of useful. It's shown up lots of interesting ways of working. I'll show you one really good example of it. Falsifiability. Imagine you get a bug reported in your system. There's a number of ways how you can proceed from that point. But your protocol, your code of conduct, how you're going to interact from that point forward is actually quite telling. So let's say, for example, I fix the bug and I write a test that shows that the bug's been fixed. Has that actually falsified that you had a system that worked in the first place? If you write the test first and see the test fail, you have now falsified that your current system does not meet its requirements. You fixed the bug, the test now passes, you've done it. That precedence, that ordering really matters. And that's fundamental falsifiability. That's science. And yet we don't follow that. Like, when we start talking about being scientists or engineers, what most people do is not science or engineering in our subject. We start to say it's craft or whatever. I would like to argue it's actually a blend of science and engineering with some craft as well, because virtually all of the other disciplines have some craft as well. But people fundamentally don't do the science. And that's often just following the right protocols, how to do it. Like, for me, I think tests have reached the stage a bit like medicine and washing hands. You would not perform surgery without washing your hands, that it would be considered unprofessional these days. A few hundred years ago, people argued about that in the medical profession. People died as a result. Thankfully, Florence Nightingale pointed out that more people died when surgeons didn't wash their hands and managed to get the point forward. And we started changing as an industry. Maybe we need to start changing. But another good example to think about, and I'll leave you with this thought. Conway's law has shown us that any software takes on the shape of the communication structure of the organization that produced that software. So thinking about how we organize ourselves, how we communicate, our protocols of interaction ends up directly reflecting in our software. So the things we do, if we fix our teams, we fix how we interact, and we start practicing that and practice the same things in our code, we tend to get much better results. And most of that comes from how we interact. It's not just us as individuals. And on that, I'll leave you. So thank you very much.